Our group used the Ames housing dataset, coupled with monthly commodity prices, to attempt to create an improved model for housing prices in the Ames area. We based our work off the 2013 study done by the Dallas Federal Reserve, which found a correlation between housing prices and commodities in commodity-dependent areas of New Zealand, as well as a similar study done by Texas A&M, which found a correlation between oil and housing prices in Texas oil towns. However, this second study suggested that there could be other lurking factors, which were likely affecting housing prices, which intrigued us. Iowa is a fairly agricultural-heavy state, so though Iowa exports other raw goods, we used only agricultural commodities in our model. In 2013, the Office of the U.S. Trade Representative reported that the top three agricultural exports in Iowa were soybeans at $3.6 billion, pork at $2 billion, and corn at $1.7 billion. All are traded as commodities, so we used them to create our own augmented model for housing prices in the Ames area. We merged two separate datasets to create our model, the Ames housing dataset and a compiled list of monthly commodity prices from Iowa State University. The Ames housing dataset from the Ames Assessor's Office tracks 2,930 home sales between 2006 and 2010 using 82 descriptors for homes and sale types. The Iowa State data tracks the local prices of pork in cart weight and soybeans and corn per bushel during the same time frame. The monthly average was used in lieu of daily or even hourly prices in an attempt to smooth out any artificial trading activity. Our general approach was to create a baseline model for home sale prices using all the quantitative variables included in the Ames housing dataset. After determining an initial R-squared value for this, we would attempt to create a simplified model using only a small handful of quantitative and qualitative variables with a similar R-squared. Once we had this initial model, we would add in the three commodity prices to determine whether or not they increase the predictive power of the model. If the R-squared value was increased by this addition, we would have evidence that the local commodities have an impact on home prices. In cleaning the data, Ames housing documentation recommended removing all homes above 4,000 square feet as they're true outliers and would detract from the precision of any fitted model which includes them. In order to do this, we had to combine several variables to find the total square footage of the home. To create this total square footage variable, we combined the total area of the basement, first floor, second floor, and garage. The correlation matrix, which we'll describe later, showed that these four variables each independently had high correlations with sale price, so the variable was ultimately used in our base preliminary model. We also created a natural log of sale price variable, since the distribution of the sale price had long tails, and the log could be used to improve the regression. The dimensions before cleaning were 2,930 cases by 82 variables, yet after cleaning it came out to be 2,925 cases by 103 variables, though many of the 21 variables added were preliminary and were used to join datasets. When first plotting the data over time, we didn't notice any similarities between the commodity prices and home prices, except that both were affected, albeit differently, by the 2008 recession. Corn and soy prices tracked fairly similarly. However, pork prices appeared to have an entirely different pattern. The climbing pre-2008 corn and soy prices were due to growing Asian markets which were willing to pay higher and higher prices. However, both commodities dipped sharply during the recession. Pork prices cannot be tracked as easily. Their extreme peaks and troughs suggest that the price swings are dictated by external influences rather than market activity as a whole. Though at first it appears that there are no similarities between commodities and housing prices, both were affected by the 2008 crash, just in different ways. Whereas commodities saw an immediate precipitous drop, housing prices slowly but steadily decreased after the crash. We considered adding a lag between commodity and home prices to our model, however we couldn't find any research which listed a documented lag time for agricultural commodities. Though the lag may have increased the predicting power of the local commodities, we couldn't find enough evidence to warrant including one, so ultimately it was excluded.
We started to find a best model for predicting the sale price by first creating a base model. We ran a base model by including all 37 possible variables from the dataset. The best multiple R-squared was 0.88, and 20 of them were significant, but they are highly correlated with each other. In order to narrow down the choice of variables from the base model, we ran a correlation plot based on all quantitative variables. Then we used the best subsets method to even further narrow down the choice of best predictors. Then we ran a regression and residual plot to show our model is valid. In this plot, the correlation between each variables is represented as a circle in the corresponding cell. The darker and larger a circle, the larger the magnitude of the correlation. We looked at the correlation between the sale price and each possible variable. We found out that overall quality, total basement area, first floor area, ground living area, total rooms above ground, car capacity of the garage, and garage area, all of which are indicated by the red arrows, are most correlated with sale price. We choose these variables for our best subset regression. From this plot, we found out that the multiple regression that includes the total square feet and the overall quality is the best model, which is pointed by the red arrow in the graph. It has a fairly good adjusted R-squared, which is 83%. Adding any more variables to the model will only be able to increase the adjusted R-squared by 1%. Then we run a residual plot on the multiple regression, which will be shown in the appendix. The residual plot shows that there are two outliers, but they are not significantly influencing our predicting power, and we will talk more about them in the later slides. After identifying the two quantitative variables we wanted to use in our model, we thought about adding categorical variables. So the three categorical variables we looked at were kitchen quality, exterior quality, and garage quality. They all had the same 5 levels: excellent, good, average, fair, and poor. We ended up choosing kitchen quality as they all improved the model by similar amounts, with kitchen quality being the highest improvement. So talking about that improvement, adding the kitchen quality categorical variable increased the R-squared by 0.01, with all levels except for poor being significant at the 0.001 level. We thought about also adding interaction terms between the 4 dummies created for the categorical variable and the other 2 quantitative variables, we thought. But few of these are actually significant, and so in our final model, none of these interaction terms were included. So using the natural log of sales price as the response variable and total square feet, kitchen quality, and overall quality as the 3 variables, we had a multiple R-squared of 0.837 and an adjusted R-squared of 0.8366, which when you compare it to our original model with all of the quantitative variables, we only see a slight drop off, which is very good for it only having 3 variables. After creating our 3 variable model, we then thought about adding commodities to the model. So we used local monthly corn, soybean, and pork prices. After adding these to the model, we had a multiple R-squared increase of 0.006 and an adjusted R-squared increase of 0.005 from that 3 variable model. In terms of coefficient significance, corn and soybeans were insignificant, but the coefficient on pork was significant at the 0.001 level.
The Flotley graphic showing expected versus observed sales price values aptly demonstrates the relationship between kitchen quality and sales price. There are clear groupings along the linear regression line based on the 5 categories of kitchen quality: excellent, good, average, fair, and finally poor. Fair through excellent fall in order along the line, however poor is somewhat in the middle due to a lack of data. There's only one occurrence throughout the entire Ames housing dataset. Beyond this, the Flotley graph shows that our model, even with commodities included, predicts sales price quite well. There are only 2 apparent outliers, even after removing the initial 5, and both are rather abnormal sales. Both sold for around $13,000, which was well below both the predicted value and the average sales price for homes in their quality and size range. Except for these 2 homes, the graphic suggests that our model fits the data quite well and has a fairly high predictive power. To determine how important the addition of the 3 commodity prices were to the model, we ran an extra sum of squares test. This test is designed to determine if variables are jointly significant to the model. The extra sum of squares test told us several important factors in the importance of the commodity prices. It improves the model's R-squared by 0.006, and it produces a p-value that was significant at the 0.01 level. This shows that the commodity prices significantly improve the model. However, we believe that there isn't practical significance to including these 3 commodity prices in the model to predict housing prices in Ames. For one, we were able to produce a very strong model using only 3 variables. In addition, adding commodities only slightly improved the explaining power of the model,
And due to the large number of observations in our analysis, even a small improvement would provide statistically significant results.
To examine the relationship between the three commodity prices and the home sales prices, we color the graph plotting the expected versus the observed sales prices by the three commodities in turn to determine if a clear pattern such as the grouping in kitchen quality could be observed. Corn prices, soybean prices, and hog prices all showed no trace of the same pattern that was seen in kitchen quality. This variation allowed us to conclude that there was no clear correlation between commodity prices and home sale prices. We found that despite having statistical significance, the commodities don't add any practical significance to the original model of square feet, overall quality, and kitchen quality. Both the correlation between the commodities and the sale price, as well as the sum of squares, were quite low, suggesting that they added very little to the model. As a result, we came to the conclusion that there is almost no relationship between the corn, soybean, and hog prices and the Ames housing market. There are several different factors which may be influencing this. Despite being in Iowa, Ames is still a college town, meaning that the housing prices will be significantly more insulated from agricultural issues than more rural areas. Secondly, as we were unable to determine a lag time between shifts in commodity prices and housing prices, even if there was a relationship, we would still likely miss it. Despite an abject failure in our prediction that local commodity prices could be a predictor for home prices, we were able to create a strong linear model with an R-squared of 0.84 using just 3 variables from the original Ames housing dataset. The predictive ability of the variables within this dataset suggests that in almost every practical application, it would be unnecessary and difficult to use outside data to attempt creation of a better model.